Git is an open source distributed version control system. That itself might not make a lot of sense to you right now, so let's break it down into some smaller parts. Let's say you're working on building a website, and after a while, you decide that the website is ready to be deployed. Your deployed website is now available on your domain, and anyone on the internet can visit it. On your own computer, you have a local version of that deployed website. After a while, you want to make some updates to the website. You change the background image and add a better subtitle to the landing page. It's not ready to be deployed yet though, it's just some draft changes that still need some other things before you actually want to deploy the updated version. Suddenly, your friend texts you saying that he spotted a typo on your website. In the navigation bar, the About button is spelled with 2 B's instead of 1. You quickly want to change it to make sure that there are no typos on the deployed website. But wait a second, we changed the background image and added a subtitle which we don't want to deploy yet. So we can't update the contents of the deployed website without overriding all the changes that we've just made locally. In this case, Git can help you out. Git is a content tracker, it stores all our code changes, and it's also a distributed version control system. A version control system basically means that we can go back in time and work with a different version of our codebase, since Git stored it all, and work with branches, which will be covered later on. Distributed means that it has a remote repository which is stored in a server, and a local repository which is stored on the computer of every developer working on a project. So every developer has access to the full copy of the codebase. Git is a version control system. We can basically go back in time without losing any new changes. When we've made changes, we can save the current state of the website. This way, you always have all your versions stored, which makes it super easy to go back in time. You have access to your entire project's history, the changes you made, who made the changes, if you're working on a project with multiple team members, and when it was made. Git can help us out to fix the button bug for the deployed website. Currently, we have 2 versions of the website, the deployed landing page and the updated landing page that contains our local changes to the background image and subtitle. We want to go back in time to the state of the website when we deployed it. With Git, we can go back in time to that state of the deployed website without losing our new changes. Git has 2 repository types, local and remote. The local repository is on your own machine, so you have direct access to it. The remote repository is usually a centralized server and is entirely optional. We can save the changes that we made locally on this remote server. The remote repository is very useful when you want to have a backup of your data in case your computer breaks or when you're working with a team. Teammates can initialize their own local repository on their own computers and simply pull the data from the remote repository in order to start working on your project. When one of the team members has made some changes, they can push these changes to the remote repository. In order to keep your local and remote repository in sync, you can then pull these changes from the remote repository into your local repository. The local repository actually consists of 3 stages. The working area are all your active changes. Git doesn't know what to do with them yet, it just knows that these files contain some updates. The staging area contains new changes that will soon be committed, and then there are the committed files. Previously, we looked at the use case of Git, and we saw that people could add their change and save new states of the project each time. What we're actually looking at here are commits. People can commit their changes in order to add version control to the project. The files that should be included in the commit are first added to the staging area. A commit gets created when a developer actually commits those files. First, let's get Git installed in our computers. You can easily find the install scripts for your specific machine on the website that's listed in the description of this course. Another way of installing Git is by using Homebrew. In that case, we simply have to type brew install git. To check whether Git has been installed correctly, we can check the current version of Git on our machine by typing git -- version. If you see a version, you've successfully installed Git on your computer. Now let's see what Git is all about and how it can help us.
Hello, my name is Mumshad Manambet, and I'll walk you through some of the demos and labs in this course. Let me show you how the labs work first. So this course is project-based. Throughout the course, you will be working as an author, part of a team, developing stories. So why stories? We have a good mix of developers and operations people as part of our audience, and we thought a generic, simple project idea would work best for all. So this way, you can spend more time working on Git and less time worrying about the project itself. The team consists of Sarah, Max, and Tej, who are authors, and an experienced writer, Tom, who will help review their work. Now, every lecture is followed by a lab activity. The labs open up right in your browser. You'll have a terminal to a workstation and a set of tasks to be performed in the quiz portal. The quiz portal gives you anywhere from 10 to 15 tasks to complete, and you'll see two kinds of tasks. The first is where you explore the environment and identify information. You'll need to use the normal Linux commands or Git commands and some logical reasoning skills to figure out the answers to these questions. And when you select the right answer, you go to the next question. The second type of tasks are real tasks that you have to perform, such as installing Git, or initializing Git repositories, or performing commits and working with branches, pushing and pulling code from remote repositories, raising pull requests, and reviewing pull requests, approving pull requests, merging code, etc. All of these are tasks that you have to perform on the lab. And once the task is complete, you can press on the check button to test your work. Your work will be tested and you'll be given feedback instantly. Now, if there is something wrong with the task that you've performed, we will tell you exactly what that was. And you can try again and fix the task as many times as you want until you get it right. Now, in case you're not able to figure out how to solve that problem, we have a hints section where we tell you exactly what you need to do. So in case you're stuck, refer to the hints section and find the relevant commands and steps that you need to do to complete the task. Once you complete the task, press the check button again and make sure that the task is completed successfully. You can also skip a question by pressing the next button here in the top right corner. Now, in our labs, we also use a lighter version of GitHub known as Git as the hosted Git service. And you can access that by clicking on this button at the top of your terminal. So this will give you a real-world experience of working with a team. And it is to this Git remote hosted Git service that you will be pushing your code for the rest of the team to access. Now, remember that this activities related to Git are not there in all the labs. We only start that after the first few labs when we really start talking about remote Git repositories. So this is not available in the first few labs. Well, that's it for now. I hope you're excited, so jump right in.
First, let's initialize a local Git repository by going into our project folder and initializing Git. We can initialize Git by typing git init. In your terminal, you can see that we initialize an empty Git repository in a .git folder. When you execute the ls-a command in order to list all the contents of the folder, including hidden folders, such as the Git folder, you can see that the Git folder has been created. Later on in the course, I'll talk more about what Git actually does and the contents of the Git folder. But for now, it's just important to understand the flow of Git. Let's add a file to our project. It's going to be a simple text file with a very basic sentence. We've just made a new file and added the text "This is a beautiful story" to it. I'm proud of my creation, and I want to make sure that I save the current state the project is in. So I'm going to save that to my local Git repository. Now that we've added the text file, let's see if Git saw that I made a change. Although we haven't done anything with Git yet, we initialized a Git repository in this project, so Git knows all of our files and their changes. You can see the status of Git by executing the git status command. Let's see step by step what this output actually means. First, on branch master. We haven't covered branches yet, however, Git allows you to work on your code and have multiple states of your codebase. Your default branch is the master branch. As we haven't made any new branches yet, we're still on the default master branch. No commits yet. Storing changes in our local Git repository is called committing. With every commit, we save the current state of the repository and show the changes that we made to it. We haven't done so yet, so there are no commits yet, as Git tells us. Untracked files. These are the files that Git knows of. However, we haven't told Git what to do with them. We haven't told it yet that we want to add it to our local repository, for example. So they're still untracked. Right now, we haven't told Git what to do with the new story1.txt file. It might be that we don't want to add that story to our local repository at all. However, I want to commit my change. Before we can commit a file, we first have to put it in the staging area. We can put it in the staging area with the git add command. You run the git add command with the files that we want to add to the staging area. In this case, I want to add the story1.txt file to the staging area, so I execute git add story1.txt. Perfect. Now it's time to commit our change. A commit records the change of a repository compared to its previous state. In this case, we didn't have any previous commits, so the addition of the file story1.txt is a change compared to its previous state. In order to commit the files that are currently in the staging area, we run the git commit-am command with a useful message right after. The -am is a flag for message. When you make a commit, it's very good practice to summarize the change that you just made in a very short sentence. This way, you can easily track down when you made certain changes, and your teammates also know what you've been doing. In this case, I'm committing my first story, so I'm going to add the message added first story. We just created our very first commit. The changes have been saved, and we can reset our project to this exact state at any point in the future.
Hello and welcome to this demo. This is an optional demo. In most cases, you should be able to just go straight from the lecture to the labs. But in case you need a bit more handholding and need to see things in action, then you may follow this demo. In this demo, we will focus on the different stages a file can be in your working area. So let's start by creating a new file named story1.txt. So I already have Git repository initialized in the story-blog directory, and we're going to create a new file named story1.txt with some sample contents. Now, when a file is created for the first time, it is always in the working area in the untracked state. If we feel that the story is ready to be committed, we can add the story to the staging area using the git add command. When you now run the git status command, we see that it is green and it is in a state named changes to be committed. That means it's in a staging state. It's in the staging area. And then we commit it using the git commit command. Now, before committing, Git needs to know who you are because all commits are recorded by the name of an author. So you must use the git config command with the user.name and user.email properties to set the username and email address of that user. When you type git commit command without any options, Git opens a text editor. Whichever is the default text editor configured is usually the VI editor. And here you provide a message, a commit message. Every commit needs to have a meaningful message that tells exactly what that commit does, very briefly. So we go to the insert mode and we type in a message, added first story, and then we save and quit the editor. As soon as we quit, the changes are saved with the commit message we provided, which can be seen here. It shows the commit message and the number of files that were added or changed and the name of the file that was committed. So what exactly is a commit? A commit stores a copy of the file in its current state. One file or a set of files that were committed. So it saves a copy of the entire file or a set of files within the .git folder. Our work is now safe. Even if the file gets corrupted or we made some changes to it that we were not supposed to, we can restore the saved or committed version of the file later. So how exactly does it save and in what format does it save? All of that we will discuss towards the end of this course in a lecture named Understanding Git. For now, just know that with each commit, Git internally stores a copy of all the files that were committed. Now, if we run the git status command, we see that the working area is clean. The next time the file is modified, it moves into a modified state. The previous version of file which was committed is still as is in the previous commit history. It is the current version of the file that's now in a modified state. If this change was accidental, then we could restore the previous version of the file from the previous commit by running the git restore command as it is shown here. So when you do that, the current version of the file is updated with the contents of the file from the previous commit. Now, since there are no changes between the current and the previous commit now, the working area is now clean again. Now, let's say we knowingly updated the file, and then we are ready to commit the changes again. And this time, we follow the same process of staging the file using the git add command, and then committing it using the git commit command. However, this time, we will use the option git commit -m to pass in the commit message. This way, we can avoid going into the text editor and then typing in the message and then coming out of the text editor, right? So we will save with the message updated first story. And now Git creates a new commit and stores a new copy of the current version of the story in that commit. The previous version we committed earlier and the current version of the file lives in Git's commit history forever, allowing us to go back in time to any previous state or commit and look at the story at that time. Now let's say we modify story1.txt like last time, but we also added a new story, story2.txt. If we check the status now, we see that story2.txt is in an untracked state as expected, and story1.txt is in a modified state. If we wish to, we could stage and commit them together. So running the git add dot command will stage both of these files at once, and then running the git commit command will commit both of these files in Git. So our new commit now has a copy of both the files we committed. In large projects, a single commit may have many such files, and Git would store a copy of all the files changed on that commit. Now that's okay if all the changes were made as part of the same requirement. So for example, if multiple files were changed as part of a bug fix or feature add operation, then this is completely okay. In this example, if both of these stories say we're part of a single series of story, and say we are adding a character to the story who should also be part of the second story, then those are a related change, right? So they should be part of the same commit. However, say these stories were completely independent, so they are not related and these should be separate commits. So let's go back to the previous state where story 2 was added and story 1 was updated. And in this case, we have two files in our working area. We don't have to commit them together. That's why we have the staging area, to allow us to stage them separately and commit them. Remember, only files in the staging area are committed. So we could first just stage story1.txt alone and then commit it with a message updated first story. And then we could stage story 2 and then commit that separately as story2.txt. So why is it important to commit separate changes separately? And one of the best practices to be followed while committing is to make each commit atomic, meaning each commit should be to solve a single problem or implement a specific feature or improvement. Each commit should have a single set of change. Now, it doesn't mean a single file. It could be multiple files, but it should be solving a single set of change. In this example, we can see that Sarah added a front page, and Max fixed buttons in navigation, and Tej added a subtitle. These are good because all of their commits do one thing. However, take a look at this example. This is a bad example because each commit has multiple sets of changes made. Sarah added the front page and also fixed a bug. But what bug? Does it have anything to do with the front page? Max fixed buttons in the navigation bar and also added a subtitle. The buttons in the navigation bar and the subtitle have nothing to do with each other, so they shouldn't be part of the same commit. Tej fixed a few bugs and made minor improvements. What bugs and what improvements? And Max made two commits to solve the same bug. That's a bad practice too. A commit was made to update the JavaScript file to fix a button bug, and another commit was made to update the CSS file to fix the same bug. They're both related to the same issue, and so they should have been part of a single commit. So why is it important to follow this best practice and to be atomic? One advantage is that it maintains a clean history for the project and one that makes sense. While working with a large team, you'll have thousands of developers and hundreds of frequent commits, and you can read the commit history and figure out exactly what that commit was for. Another advantage is that Git, being a version control system, allows you to go back in time and revert a particular commit. For instance, say we realized that the subtitle added by Tej resulted in a new bug on the website, and we can easily revert that commit alone and restore the state of the website. And how to do that, we'll discuss that in one of the upcoming lectures. But for now, just know that that is a possibility with Git. However, in the other example, if we tried to revert the commit that added the subtitle, we would also be reverting the fixes applied on the button in the navigation bar. But we do not want to revert those changes. We only want to revert the change on the subtitle. So it's always recommended to keep your commits atomic and name your commits with a message that tells exactly what that commit does. Now let's say we add a new line, line 4 to story 1. And as expected, it's now in a modified state. And then we stage that using the git add command. And we can see that it is now staged for commit. Now before committing, let's say we make another change to the file. Say we accidentally overwrote the contents of the file. Now if you check the status now, we see that story 1 is staged and also modified. So why is that? Why is the same file in two different stages? Well, when you stage a file in Git, it caches the state of file when it was staged, meaning even before we commit a file, where we know an entire copy of the file is saved. As soon as a file is staged, a copy of the file is preserved or cached as well. So as soon as you stage a file, you're safe. In this case, I can restore the state of the file when it was staged using the git restore option. So now we have restored the file to the state that it was in when we last staged it. Let's look at another example. Say in the current state, we have story 1 in the staging area, and we update story 2 now. Story 2 is now in a modified state while story 1 is staged. So let's say we want to stage and commit the changes to story 2 first, before we actually commit story 1. So we basically need to move story 1 out of the staging area and then move story 2 into the staging area. So how do we do that? Now we can remove a file from the staging area using the command given here, which is git restore -- staged option. So we run the git restore story1.txt command with the staged option. So now both story 1 and story 2 are in a modified state. We took story 1 out of the staging area. And then we will now move story 2 to the staging area and then commit it by running the git add command and the git commit command. Now let's look at another use case. Let's say we add a personal file called notes.txt, where we decide to store our ideas. Now this file is now in an untracked state, as it's a new file. Now while staging the modified story1.txt file, we accidentally add the notes file as well, because we ran the git add command. Now if you check the status, we see that both these files are staged. And if we do a commit now, both of these files would be committed. However, we don't want notes.txt to be part of the Git repository. It's a personal file that we're going to use to store our ideas. So we can remove a tracked file by running the git rm command. Now you must specify a file name. In our case, it is notes.txt. And you also must specify one of the options, either cached or force. Now specifying the cached option will retain the file in our directory, and the force option will delete the file permanently. In this case, I have written down some ideas for the story in my notes file, so I don't want to delete it. I want to keep the file, even if it is removed from the Git's tracking. So I will use the cached option while removing the file from Git. Now if you see now, we're back to the previous state where the file is still in our directory. And when we run the git status command, we see that it's in an untracked state. So this is good, but it's not very good because there are chances that we might accidentally check in this file with Git, as we just did before. So to instruct Git to permanently ignore this file, we use a .gitignore file. We add the name of the file to a new file called .gitignore, and now in the git status command, we do not see the notes.txt file anymore. However, we do see the .gitignore file because that is also a file that Git sees as a new file. So it is a recommended practice to save the .gitignore file itself in Git, so that when you share the repository with others, the team can add commonly ignored files to this file, such as the cache directories, log directories, temporary build files, etc. Right? So, well, that's it for now. Head over to the labs and practice these by yourself.
You can see the commits that were made to the project in your terminal. The command Git Log shows the information that you need to know about all the commits, such as the commit hash, the author name, the date of the commit, and the commit message. We'll talk more about the commit hash and what it means later on in this course. If you don't care about all this extra information about the commit, you can easily show it as one line with a -- one line option. There are actually many ways to visualize our commits with the git log command. Throughout the course, I'll show some different configuration options for the different use cases. So far, we've simply added and committed all our changes. However, we've actually committed those changes to something called a branch. As mentioned before, this branch is called master by default. Now, let's say that a new developer joins the project and wants to add a new story. We don't want developers to directly make changes to our production code, but instead give them a separate version where they can change code and commit to until their work is done. In the meantime, we can keep on working on our own branch. Only after their entire work is done and tested, we want to get the new code into the production code. What we're actually saying here is that we don't want to always work on the master branch, but keep our project versioned using branches. A branch is basically a pointer to the last commit. If you're working on a new feature, you might work on a branch called feature/signup. And only once that feature has been finished and entirely tested, we want to get all those changes into the master branch. First, let's create a new branch. We can do so by running the git checkout-b command with the name of the branch. Say that the developer is called Sarah, and we just create a Sarah branch. To see a list of all our branches and the branch that we're currently on, we execute the git branch command. Currently, we have 2 branches, master and Sarah. In total, we've made 1 commit, initial commit. They both point to that commit. As stated before, branches are actually nothing more than pointers to a certain commit. Now let's say that Sarah adds a new story and commits this to the Sarah branch. This commit gets added to the Sarah branch, but not to the master branch. The master branch is now 1 commit behind the Sarah branch. Let's say that the team is growing and you just hired a new developer. This developer, called Max, wants to write the 3rd story. Max is currently still checked out on the master branch, but to keep things clean, Max also creates his own branch called Max. Max writes the 3rd story and commits this to his Max branch. The Sarah and master branch don't have this change yet. Only Max's branch has this change. Here are some useful commands that you can use when you're working with branches. In order to create a new branch, you can run the git branch command with the name of the new branch. You can switch branches with the git checkout command, followed by the name of the branch to which you want to switch. To create a new branch and immediately switch to this new branch, you can run the git checkout-b command. This command combines the git branch and git checkout command together. And to delete a branch, run the git branch-d command. The -d flag stands for delete. And to list all the branches that you currently have, you can run the git branch command. Now that we've talked about branches, it's important to know what a head is. You might see the reference to head in quite a few places. A head is where you are right now in the Git repository. The head points to the last commit in the branch that you're currently on. When you switch branches, the head moves with you. If you're working on a new feature, you might work on a branch called feature/signup. And only once that feature has been finished and entirely tested, we want to get all those changes into the master branch. We can merge a branch with a git merge command. The git merge command receives the name of the branch that we want to merge into our current branch. In this case, we first have to check out to the master branch in order to merge feature/signup into master. We can now merge by typing git merge feature/signup. There are 2 types of merges that Git can perform: a fast forward merge or a no fast forward merge. A fast forward merge can happen when the current branch has no extra commits compared to the branch that we're merging. Git is lazy and will first try to perform the easiest option, the fast forward. This type of merge doesn't create a new commit, but rather merges the commits on the branch that we're merging right into the current branch. Since the master branch doesn't contain any extra commits, we can merge the branch directly into master. Perfect! We now have all the changes that were made on the branch available on the master branch. So, what's the no fast forward all about? It's great if your current branch doesn't have any extra commits compared to the branch that you want to merge, but unfortunately, that's rarely the case. If we committed changes on the current branch that the branch we want to merge doesn't have, Git will perform a no fast forward merge. With a no fast forward merge, Git creates a new merging commit on the active branch. The commit's parent commit point to both the active branch and the branch that we want to merge. No big deal, a perfect merge. The master branch now contains all the changes that we've made. That's it for this lecture. Head over to the labs and start practicing what you've just learned. Previously, we saw it's possible to have a remote repository with Git. We can push code to this remote repository that is hosted somewhere else and get this code again on our local machines by pooling this information. There are several platforms on which we can host our remote repository. The most commonly used platforms are GitHub, GitLab, and Bitbucket, but there are also many more out there. Once we've successfully initialized a repository on one of those platforms, we get access to something called a connection string. A connection string is a URL that we can use in order to let Git know where the remote repository is located. We can add the remote repository to our local project with the git remote add command. We want to add a remote repository and give it the alias origin to make sure that we always know which remote repository we're pushing to without having to memorize the entire connection string. In order to do so, we can type git remote add origin, followed by the connection string. After initializing the remote repository, we have access to this remote repository that is hosted at the location of the connection string. You can list all your remote repositories with the git remote-v command. In order to work with this remote repository, we can fetch and push the necessary data from our local project to the hosted repo. In this case, we're both pushing and fetching data from the same remote repository, which Git shows us. First, let's see how we can push data to this remote repository. In order to keep our local and remote repo in sync, we have to push the data from our local repo to the remote repo. We can push data to a remote repo with the git push command. This command expects two more arguments: the alias of a remote repo, which we called origin in this case, and the current branch that we're on. We haven't made any Git branches yet, so we're just on a default branch named master. It can happen that we've made some new commits locally that we haven't pushed to the remote repository yet. In this case, the remote repository is not in sync with the local repo. By using the git push command, we can push the newly committed files to the remote repository. Now that we've pushed the new data, any developer that has access to our remote repository can fetch the latest changes that we just pushed. When a new team member gets added to the project and should get access to all the data that's currently hosted on the remote repository, that person can clone the repository in order to get all this data on their local machines. You can clone a repository with the git clone command, followed by the SSH link of the remote repository. So let's see how we can get that SSH link. Each platform has a different UI and a different way to access the SSH link in order to clone the repository. But in this case, let's just focus on the most popular platform, GitHub. When visiting the remote repository, you see a big green button with the text clone. Once you click on that button, you see a flyout with the SSH link that we need in order to clone the repository. We can now clone it locally on our machine with the git clone command, followed by the SSH link that we just copied. By default, it'll create a folder locally with the same name as the remote repository, which you can see here. Let's go into the folder that was just cloned with the cd command. When we type Git Log, you can see that we have the entire Git's history of the project that we just cloned. We can now get started to work on this project locally and interact with the remote repository when we've made changes in order for the entire team to stay up to date. In the previous examples, we saw that we could merge branches directly into the master branch by first checking out to master and then merging them. When you're working with a team, however, you usually don't want to do this. Instead, we can do all of this on a platform like GitHub. In order to push the latest change to GitHub, we'll push to the origin Sarah branch by typing git push origin Sarah. After pushing to the Sarah branch and checking out the GitHub repo, you'll see a pop-up that shows that the master branch is now one commit behind the Sarah branch. In order to merge Sarah into master, we'll have to open something called a pull request. We can do that by clicking the pull request button in the top bar or the pull request button shown in this pop-up. Once we've clicked on that button, you'll see the changes that were made to the Sarah branch compared to the master branch, and a button to create a pull request. Let's create a pull request, also called a PR. We can add additional information about the changes that we've made, such as a title and a description, maybe some important labels, or add specific reviewers for this pull request. Now that the pull request has been opened, other team members can see the changes that you've made and comment on them. If everything has been approved, you can merge your changes into master by clicking the Merge Pull Request button. Perfect! Instead of checking out to master locally and merging it that way, we've just merged our changes into master by creating a pull request and merging it on GitHub. The origin Sarah branch has now been merged into the origin master branch. To make sure that not anyone can just merge changes into the master branch, you need to have the right privileges to do so. This is the default if it's your own repo, but if you're working in a larger team, you may need to ask other team members to merge the PR for you. We just updated the origin master branch by merging origin Sarah into it. Our local repository isn't automatically aware of these changes, so we'd have to get these changes into our local repository. We can do so with the git fetch command. We can type git fetch master in order to update the origin master branch in our local repo. Now that we've fetched the origin master, we can update our local master branch to point to the latest changes made on origin master. To do that, we can merge origin master into the local master branch. Awesome! We now have all the latest changes available locally. Instead of individually fetching and then merging, we can also pull the origin master branch with the git pull command. Git pull is actually two commands in one, git fetch and git merge. By typing git pull origin master, we can fetch and merge the remote changes directly into our local master branch. That's it for now. It's time to gain some hands-on practice. In most cases, Git is smart enough to know how files should be modified when we're merging branches. However, that's not always the case. Imagine that Sarah started working on the 4th story. But she didn't communicate this with Max, so Max also started working on the 4th story. Sarah was a bit quicker though, and merged her changes back into master. Max now wants to go ahead and merge his change into master as well. But the master branch contains changes compared to the Max branch in a file that we're currently trying to merge. However, the file within master says this is Sarah's version, whereas Max's version says this is Max's version. Git doesn't know which version you want to keep. And we just ended up in a merge conflict. There are several ways to resolve those conflicts, for example in Git GUIs, or simply in the code editor. During a conflict, Git adds some extra characters to the file that's conflicting. Git shows the current context of the conflicting files, as well as the contents that we're trying to merge. We can simply remove the lines that we don't want to keep and leave the lines that we do want to keep, and then save the file again. During the conflict, we made some changes to the fourth story.txt file, which we'll have to add to Git again. After adding it, we can finally merge the Max branch without any conflicts. Master now contains a combination of Max's and Sarah's changes. So far, our examples used a small team of individuals working together. Since it's a small team, all members of the remote Git repository had the right permissions to push their changes right in. However, this isn't always the case. There are thousands of open source projects on GitHub with millions of contributors contributing to them. All of these contributors are not members of these projects with right permissions. We don't want just anyone to be able to modify our code, of course. So how do you create a pull request if you're not part of the Git project and therefore not allowed to create branches or push your changes right in? One way to contribute to such projects is to first fork the main project. After forking the project, you can add your changes to a branch on the forked copy and send a pull request to the original project to merge your changes right in. When you fork a Git repository, you're creating your own copy of the original project. You're free to experiment with it and do whatever you want to do with the repository without impacting the original project. Once you think that you have something to contribute to the original project, you can create a pull request safely. The reviewers of the original project can now review the changes submitted by you and give feedback to you if required. Once your PR has been approved by the maintainers, they can merge your changes into the original repository. You've now successfully contributed to an open source project. Sarah has been working on her own story in her own branch. Since it's quite a long story, she's been at it for a while. In the meantime, her team has been making progress and have been contributing additional stories and updates to the master branch. Sarah wants to make sure that her branch is all caught up with the latest changes from master. One way to do that is to merge the master branch into her own branch. This creates a new merge commit to merge these changes into her own branch. Another way to achieve this is by rebasing branches. When we are rebasing branches, we're basically putting one branch on top of another one. Let's rebase the Sarah branch on top of the master branch by typing git rebase master. Awesome! Instead of merging the branch into master, we've moved the Sarah branch on top of the master branch. The Sarah branch now contains all the changes that were made to the master branch. Although rebasing is an effective way of getting changes from one branch into another, there are some more differences compared to merging. In Git, each commit has a unique identifier. This unique identifier is a hash that contains information about the commit and makes it possible for us to interact with the specific commits. When we merge branches, these unique identifiers won't be modified. In other words, we are not modifying the history of our Git commits when we're merging. When we rebase branches, however, we're actually copying the commits from one branch to another. Since we're creating new copied commits, the hashes update. In other words, we are modifying the Git history when we are rebasing the branches. And although this isn't always a problem, it can be annoying when you're working with a team. It's not clear when certain branches got rebased, since there is no merge commit. The rebase command also allows us to modify the Git history on a certain branch before rebasing it. Let's say that we've been working on the Sarah branch, but there are many commits that should actually have been just one commit. All the changes to the second story commits should have been added to the added second story commit. We can change the history of a Git branch with an interactive rebase. We have access to this through the -i flag in the Git rebase command. We have to specify which commits we want to update. In this case, we want to modify the first 4 commits. By passing the head-4 value, we're telling Git that we want to interactively rebase the last 4 commits. After typing this commit, Git shows you a lot of information. In here, we can specify how we want to change the commits. You see that Git helps you out by showing which commands are available when rebasing interactively. In this case, we want to use the squash command to melt the 3 commits into the first commit. In order to squash the commits, we have to change their commands from pick to squash. After changing the commands, we can save the changes and exit. We've now successfully rebased the 3 extra commits and created a new commit that contains the changes of all 4 commits combined. Although I just only showed the squash command, there are so many other options when you're interactively rebasing. It's a very powerful tool to make changes to your branch and commits. It can happen that one branch has a commit with a certain change that you'd like to apply to another branch, but you don't want all the changes that were made to that branch. In this case, we can cherry pick that certain commit in order to create a copy of that commit onto our own branch. Let's say that we're on the master branch, and we want to add the changes that were made to the changed first story commit on the Sarah branch. In that case, we can cherry pick the commit with the git cherry pick command and the hash of the commit that we want to cherry pick. Awesome! We now have a copy of that commit on the master branch. Everyone makes mistakes, and it can happen that we have committed certain changes that we actually didn't want to commit. In that case, we have several options to undo that commit. The first option is to revert it. Let's say that we want to revert the commit where we added the third story. The git revert command creates a new commit, which literally reverts all the changes that were made on the commit that we specified. In the added third story commit, the thirdstory.md file got added. The reverted commit contains all the opposite changes. It deletes the thirdstory.md file. The revert command is useful if you want to undo changes and keep those changes in your Git history. Another way of undoing changes is with the git reset command. There are 2 ways to reset the commit in order to undo it, either with the --soft flag, in which case we still want to keep all the changes that were made, or with the hard flag, in order to lose all the changes that were made on that commit. First, let's reset the added third story commit with a soft flag. The reset command also receives the amount of commits that we want to reset, 1 commit in this case. The added third story commit has now been reset, and the Sarah branch is now pointing to the changes to second story commit. Since we reset the commit with a soft flag, we still have access to the changes that were made by that commit. We can see this when we type git status. Perfect! Although we just reset the commit, we still have access to all the changes that this commit introduced. We can easily create another commit this way. If we were to reset the added third story commit with the hard flag, the commit will be reset without saving all those changes. The third story file is now completely gone. Well, that's all for this lecture, and I'll see you in the next one. Let's say that we're working on the third story on the Sarah branch. Suddenly, a friend tells us that there is a typo in the first story on master that quickly needs to be fixed. Before checking out to the master branch, we need to put the changes that we made to the third story somewhere to have a clean working area if we want to fix the typo on master. Since the story isn't done yet, we don't really want to commit it to the Sarah branch. In this case, we can use git stash. We can stash all changes in the working area with the git stash command. The modifications in the working area all get added to this stash. With the git stash pop command, we want to get the changes back into the working area. You can see the stash as a pile of books. We can keep on pushing to the stash and the changes will simply pile up. If you want to see all the stashes that are currently on the stash, you can use the git stash list command. You can see the contents of a certain stash with the git stash show command, followed by the stash that you want to see. If you want to pop a specific stash instead of the last one that was added onto it, you can execute the git stash pop command with a specific stash. That's it for this lecture. Head over to the labs and start practicing what you've just learned. Everyone makes mistakes, and that's totally okay. Sometimes it may feel like you've screwed up your Git repo so badly that you just want to delete it entirely. Sarah was convinced that she made a commit that wasn't necessary at all anymore, and performed a hard reset on that commit. Suddenly, she realized that this commit actually was important after all. However, since this was a hard reset, it seems like all this data is gone forever. Well, no need to panic. The Git Reflog command shows us all the actions that have been taken on our repo. This includes merges, resets, reverts, basically any alternation. If you made a mistake, you can easily undo this by resetting head based on the information that Reflog gives us. Sarah wants to undo her hard reset. When we execute the git reflog command, we see that the state of the repo before the hard reset is at head 1. Let's perform a git reset to point head back to where it was on head 1. Awesome! Our repo has been reset to its previous state. We can also see that this action has been pushed to the reflog. We've seen a similar command earlier in the course, the Git Log command. Although Git Reflog and Git Log may look similar, Git Log will only show you the information about the commits, and not about the state of the repository like Git Reflog does. Now that we've seen how we can interact with Git, let's take a look at how it actually works. Git is nothing more than a key value store. When we add a file to a commit, the contents of the file are hashed using the SHA-1 algorithm. The hash is then used as a key name for the folder and stores the file using that key name. Git has porcelain commands and plumbing commands. Porcelain commands are commands like git add, git status, git commit. They're easy for the user to remember. With plumbing commands, you get access to the internals of Git. Using some of Git's plumbing commands, we can create the hash ourselves. This is usually what happens when we execute the git commit command. Let's say that we have a firststory.txt file with a very short sentence. With the hash-object command, we can hash the contents of this file, followed by the name of the file that we want to hash, the firststory.txt file in this case. You can see that Git returned a hash. The first 2 characters of this hash are used as the key. This is the name of the folder that stores the contents of this file, the value. If we committed the first story.txt file, the exact same hash will be created. Git then creates a folder called BE. This is visible when you open the .git folder, which gets created when you run git init. You can see that there are some folders within this folder, and one of them is named BE. When you access this folder, you can see that the value of the hash is stored in here. In order to see the contents of this hash, we can use another plumbing command called catfile. We can add a flag to this command, -p, in order to pretty print the contents. We can use the catfile command with the first couple of characters of the complete hash, BEA8D7 in this case. We just got the contents of our first story.md file back. This is almost identical to what a commit is. However, in a commit, there is a little bit more information. Let's catfile the commit instead. You can see that the contents of the commit contains a bit more info than just simply running catfile on the hash that was generated by the hash object command. We also have information about the tree, the parent, the author, and the committer. The author is the user that authored the change. The committer is the user that actually committed the commit, and the parent is the parent commit. Now, let's talk about the tree. Folders in the object folder can be of 3 different object types. It's either a commit, a tree, or a blob. A commit is simply a commit. A tree is a folder on your file system that is associated with that repository. And a blob is basically just a piece of data. Previously, we hashed the first story file using git hash object. The first story.md file is called a blob. It's just a piece of data. It's not a folder nor a commit. When you've made multiple commits, you get a structure like a tree. Every commit points to their parent commit. It's actually also a lot more than just a tree. Each commit actually holds a reference to more trees and blobs. The first commit points to a folder in the Git repo with just a simple blob, for example, our first story.md file. The second commit points to a bit more information, a folder in the Git repo with a reference to the previous blob and a new one. The new blob could be the second story.md file, for example. The third commit points to the new second story blob and a new blob, maybe the third story.md file. As you can see, a commit basically just stores a reference to a folder structure. This is why we have version control in Git. We can simply go back to a commit that points to different blobs and trees. Well, that's all for this lecture, and I'll see you in the next one. That was a lot of new information. Let's do a quick recap of all the new concepts that we've learned. First, we saw how we could install Git and initialize it in our project. We also saw that Git created a hidden .git folder after initializing it in our project, which Git uses to store data. We also covered how we could initialize a remote repository to save our data on a remote server and potentially work with teammates. We saw that we could push our local data to this remote repository with the git push command and clone a remote repository onto our local machines with the git clone command. Then we covered how we could work on our own version of the project by creating a branch. When we've made some changes, we can commit these changes to our branch and merge these changes back into other branches. Besides merging, we also covered the possibility to rebase the changes instead, which creates a different Git history compared to merging. To get more control over the commits that we're rebasing, we can perform an interactive rebase and change the commits before rebasing them. We also saw how we could undo changes by reverting or resetting our changes. Whereas reverting changes creates a commit that literally reverts the changes that we've made, resetting is a bit more harsh. If we reset the changes with a soft flag, we'll still have it in our working area. However, if we reset the changes with the hard flag, all changes are lost. Being able to work with a team is a great benefit of using Git. We saw how we could open pull requests on platforms such as GitHub, where teammates can review our changes and potentially request changes. Git is an extremely powerful tool. I hope that this course has given you a good introduction to its main concepts, and that you'll feel more confident using Git in your projects. Don't forget to leave a review. If you have any feedback, please do let us know. Until next time, goodbye.